Hi friends, welcome to our YouTube channel Knowledge Academy. The main aim of this playlist is to teach or discuss the formulas of mathematics in a very detailed manner. If you are seeing this video lecture for the first time in the YouTube channel, then please do like, share and subscribe to the YouTube channel, and don't forget to press the bell icon button. So whenever you upload a new video, the direct audience comes to your mobile. So why waste more time? So let's get started. So now in this lecture we will learn some of the points in the matrices. See, the first point is here. See, in a square matrix all the elements in the diagonal are called as the diagonal elements. In a square matrix all the elements in the diagonal are called as the diagonal elements, and sum of diagonal matrices is a diagonal matrix, and the product of diagonal matrices is a diagonal matrices. Sum of lower triangular matrices is also a lower triangular matrix, and the product of lower triangular matrices is also a lower triangular matrix. And similarly, the sum of upper triangular matrices is also a upper triangular matrices, and the product of upper triangular matrices is also a upper triangular matrices. So now here, see, if you multiply the matrix A with identity matrix, whether you do it in this process or whether you do it in this process, always the answer is A. Means if you multiply the identity matrix with any other non-zero matrix, then the answer will be a non-zero matrix itself. See here, suppose there is some square matrix n cross n. For this square matrix, suppose this matrix is going to satisfy a symmetric matrix. Suppose this matrix is a symmetric matrix, means for the symmetric matrix A transpose has to be equal to A. Then only that matrix is said to be a symmetric matrix. So now we are going to figure out how many different elements we can put in this matrix. See, in the symmetric matrix, whatever the element in this will be always equal to this. Similarly, whatever the element in this will be equal to this. Means whatever the elements in this are kept in same process in this manner. So therefore in the first row the number of elements, different elements we can put is n. Similarly in the second row, because these are diagonal elements, right? So these are the two elements, right? Means one element we need to subtract from the total n, because the matrix is n by n, means n number of elements in the row. So therefore n minus 1. So if you go, suppose same manner we have to go like this up to 1. So therefore the elements in the first, the number of different elements we can keep in the first row is n, and the number of different elements we can keep in the second row is n minus 1, and similarly the number of elements kept in the third row is n minus 2, and it goes on the same fashion up to the last row. So therefore the last row, the number of different elements we can put is 1. Means what I am trying to say is all these elements in this side are going to be different, means they are not equal in any manner. So therefore if you do the summation m plus n minus 1 up to n up to 1, if you do this one, this is called as this series is in a 1 plus 2 plus, or we can write in another fashion 1 plus 2 plus up to n minus 1 plus n. So if you do this one, you will get n into n plus 1 by 2. So sum of n numbers is a n into n plus 1 by 2. So therefore the number of different elements we can keep in a symmetric matrix formula is of order n by n is n into n plus 1 by 2. So therefore the other formula is A into A inverse, or A inverse into A is a identity matrix. So therefore if you multiply any matrix with inverse of its matrix, if you do in this fashion or in the reverse fashion, always the answer will be identity matrix. See, suppose the another point is, for any matrix A we can split into a symmetric matrix and a skew symmetric matrix. Any matrix of square, this matrix always has to be a square matrix. Any square matrix can be split into sum of two matrices, which are, this one is called as a symmetric matrix and this is called as a skew symmetric matrix. Means this matrix is going to satisfy the symmetric property and this matrix is going to satisfy the skew symmetric property. So the formula of the symmetric is half of A plus A transpose, and the skew symmetric is half of A minus A transpose. See, now we move forward. Here we already know A inverse. A inverse is equal to adjoint of A by modulus of A. Modulus of A is also called as the determinant of the matrix. So adjoint of matrix A is equal to cofactor of matrix A whole transpose. Means what are the cofactor of the matrix we got, then we need to do the transpose of that matrix, then it's said to be the adjoint of the matrix A. This the inverse will apply for a given matrix only when the determinant of the matrix is not equal to 0. Suppose if the determinant of the matrix is equal to 0, then anything by 0 will be infinity. Means the inverse of the matrix does not exist when the determinant of the matrix is equal to 0. So whenever the determinant is not equal to 0, we call it as a non-singular matrix. If determinant of the matrix is equal to 0, then we say it to be a singular matrix. See, suppose this is a 2 by 2 order matrix. A is equal to A, B, C, D. This is a 2 by 2 order matrix. So if you want to figure out what is the A inverse, we can do in this fashion and you will get finally the result will be A inverse is equal to D minus B minus C A by determinant of the matrix is AD minus BC. Do the product of the opposite arms and keep a minus symbol between them. So the another property is I inverse. If you do the inverse of identity matrix or whether you do the transpose of the identity matrix, the result will be always a identity matrix. So solution, zero solution for any matrix. Zero solution means 0, 0, 0 is also called as a trivial solution. See, in any question if they give this question has whether this question has a trivial solutions or not, means they are asking whether these equations are satisfied zero solution. Whenever any zero solution satisfies any equation, we say that the equation has a trivial solution. If any equation it is having non-zero solutions, if these are satisfying the equations, then we call it as a non-trivial solution. So finally what I am trying to say is zero solution is also called as a trivial solution and non-zero solution is also called as a non-trivial solutions. Trivial solutions are exist only for the homogeneous equations. This is already I explained in my previous lecture. Trivial solutions are always exist for a homogeneous equations, but trivial solutions are not exist for non-homogeneous equations. These all things I explained in my previous lecture. If you are not seen the previous lecture, then please go back to this playlist and see the lectures from the starting. What is meaning of the dimension? Dimension means number of independent vectors in a matrix. Number of independent vectors in a matrix, or in another fashion we can easily figure out dimension is equal to rank of a matrix. Rank of a matrix itself tells number of independent rows or number of independent columns in a matrix. So therefore finally what I am trying to say is dimension. Dimension of any matrix is equal to find the rank of the matrix. The rank of the matrix itself tells what is the dimension of the matrix. So dimension of the matrix is equal to number of independent vectors in a given matrix. That is called as the dimension of the matrix is equal to the rank of a matrix, because rank of a matrix directly tells what is the number of independent row vectors or number of independent column vectors in a given matrix. So in another fashion, if we know what is the dimension of a matrix means number of independent row vectors. So now we need to figure out what is the number of dependent vectors. Means out of total number of rows, out of total number of vectors minus number of the independent row vectors, then finally we will get number of dependent vectors. See, there is another word for the dependent vectors, which is null of a matrix. See, in any question if they are asking what is the null of a matrix means, null of a matrix means number of dependent vectors in a matrix. So we can figure out what is the number of dependent vectors in a matrix is equal to total number of vectors in a matrix minus rank of the matrix. So rank of a matrix will always tells what is the number of linearly independent row vectors or column vectors. So that is the reason we are subtracting total vectors minus independent vectors. Then we will get what is the dependent vectors in a matrix. That is the another word for dependence is the null. Null of a matrix, if they are asking me, the question says that what is the number of dependent vectors in a matrix. See, for eigen, I have already told in my base lecture, eigen vectors are always non-zero vectors. Eigen vectors are always non-zero vectors. Eigenvectors are always non-zero vectors. For triangular matrix, for a triangular matrix, the number of for a triangular matrix, the diagonal elements itself are the eigenvalues. I am repeating it again. For a triangular matrix or for a diagonal matrix, the eigenvalues are the elements in the diagonal of a matrix. See, for orthogonal matrix, I have already told you. For orthogonal matrix, the property is A into A transpose is equal to identity matrix. If any matrix satisfying the condition A into A transpose is equal to identity matrix, then that matrix is said to be a orthogonal matrix. So for orthogonal matrix, if you want to discuss about the eigenvalues, suppose if lambda is the eigenvalue of a orthogonal matrix, then compulsory 1 by lambda is also a eigenvalue of the orthogonal matrix. Means the reciprocal of the eigenvalue is also a eigenvalue of a orthogonal matrix. I am repeating it again. For a orthogonal matrix, the condition is to satisfy is A into A transpose is equal to identity. If any matrix satisfying this condition, we can blindly say that this matrix is a orthogonal matrix. So if lambda is the eigenvalue of orthogonal matrix, then compulsory 1 by lambda is also a eigenvalue of the orthogonal matrix. See, for a symmetric matrix, we have already told you the symmetric matrix has to satisfy a condition which is A into A, J is equal to A transpose. If any matrix satisfying A transpose is equal to A, just transpose of matrix itself is equal to the same matrix, then we can blindly say that that matrix is a symmetric matrix. So for a symmetric matrix, the eigenvalues, for a symmetric matrix, if you figure out the eigenvalues by a characteristic equation, we will get always the real number. For a symmetric matrix, the eigenvalues are always real numbers, whether they can be equal or whether they can be distant or whether they can be positive or whether they can be negative. In these four things, anything can be possible. I am repeating it again. For a square matrix, for a symmetric matrix, the eigenvalues are always real, whether they can be distinct, means not equal, or whether they can be equal also. That case, that condition can also be possible, or whether they can be positive or whether they can be negative. Anything can be possible for a symmetric matrix. See, one more thing is, I have already told you, rank of a matrix of matrix A is equal to rank of the transpose of the matrix. Rank of matrix A is equal to rank of even transpose, means whether you do the transpose of the matrix or whether you take the original matrix, if you figure out what is the rank of the matrix, the rank of a matrix doesn't change because transpose itself means that changing the rows to the columns or changing columns to rows. So therefore rank tells you the number of linearly independent vectors, whether it can be row vectors or whether it can be column vectors in a matrix. So by doing the transpose, then nothing will change. So therefore the rank of the matrix is equal to its transpose also. Here same thing for the eigenvalues. So eigenvalues of matrix A is equal to the eigenvalues of transpose of matrix, because by doing the transpose the eigenvalues doesn't change us. So therefore blindly we can say that the eigenvalues of the matrix A is equal to the eigenvalues of the transpose of this matrix. All these things I have discussed in the previous lecture. This is just whatever the points which I have discussed, which have some points I have missed and some points which I have already covered. So therefore all these things I am going to cover in this session. So therefore the another thing is, the one best property of transpose is even the determinant is also equal. The determinant of matrix A is equal to the determinant of the transpose of the matrix. Means blindly three things are equal. The rank of the matrix, whether you do the original matrix or whether you do the transpose of the matrix, both are equal. And also the eigenvalues of the matrix A is equal to the eigenvalues of the transpose of the matrix. And similarly the determinant of the matrix of A is equal to determinant of the transpose of the matrix. So therefore these three conditions for the original matrix and the transpose matrix are always equal. Now for elementary transformation, we have discussed elementary transformation. Only the first elementary transformation will change as the determinant of the matrix, and the second elementary transformation will change as the determinant of the matrix. So by doing the elementary transform of a matrix, then we will get a matrix. In this new matrix, the eigenvalues doesn't changes with the original matrix. So what I am trying to say is, you apply any of the elementary transformation, whether you apply first elementary transformation or whether you apply the second elementary transformation. So by doing these elementary transformations, we will get a new matrix. For this new matrix, one thing is same, which is eigenvalues. Eigenvalues doesn't changes. Eigenvalues doesn't changes for the new obtained elementary. After doing elementary transformation, we will get a new matrix, right? For this new matrix, the eigenvalues doesn't changes with respect to the original matrix, but determinant can change. If you apply the first elementary transformation, then determinant will compulsory change, but not the second elementary transformation. So if you apply only the second elementary transformation of a given matrix, then the determinant doesn't changes. But in case you apply the first elementary transformation, then be careful that the determinant of the matrix will change. But eigenvalues, whether you apply the first elementary transformation or whether you apply the second elementary transformation, the eigenvalues of the new obtained matrix are same as the original matrix. So some more points we will discuss in this lecture. See here, matrix P. Suppose for this matrix P and Q, the order of the matrices M cross R and R cross N. So after doing the multiplication, we will get a new matrix A, which is order is M cross N, because R is common, right? So therefore the uncommon terms are M and N. So therefore M cross N. So for this matrix, the number of multiplications which are there in this matrix, whether if you are doing product, means we need to do the row and the column. This row of the first matrix and the columns of the second matrix, we need to do the multiplication and then we need to do the addition. So for each and every element, if you want to figure out, then we need to do the first the multiplication and then you do the addition. So he is asking how many times you are multiplying, means the number of multiplications are there in this product is M into R into N. So just do the M R N, because R is common, right? The M R N. This gives the number of multiplications which are present in this product, which is M into R into N. So therefore, suppose in any two dimension, 3 points are there, x1, y1, x2, y2 and x3, y3. Suppose by these 3 points we can draw a triangle. So therefore area of the triangle, so many different formulas, area of a triangle. There are a lot of formulas, but I am going to discuss only one small formula, which is area of the triangle is equal to half of, this is determinant, right? This is modulus. Modulus means always a positive number. Modulus means whatever, suppose by doing these calculations, if you get a negative number, then always the modulus will be always the positive, means whatever the quantity, if it come outside, it has to be a positive number, because area will be always a positive quantity but not a negative quantity. So therefore x into y2 minus y3 plus x2 into y3 minus y1 plus x3 into y1 minus y2. So easy way to remember this formula is, first write x, and the bracket terms are always y terms, and The pattern is 1 2 3, next 2 3 1, next 3 1 2. This is the fashion of writing this formula to remember. See, I've already told you, for upper triangular matrix or with a lower triangular matrix or with a diagonal matrix. For these three matrices, the eigenvalues itself are the diagonal elements. So whatever the diagonal elements itself tells the eigenvalues of the matrix. So for these three matrices, it is very easy to figure out the determinant of the matrix, because the diagonal elements are itself for the eigenvalues, and this do the product of all the eigenvalues, then we will get the determinant of the matrix in a very easy fashion. And suppose, see, after doing some simplification, if the determinant of a matrix is positive, if determinant of a matrix is positive, then it means that all principal minors are positive. If all principal minors are positive, suppose if you got, I have already told you what are the minors. So if all the principal minors are positive, then definitely one thing is correct. That is, the determinant of the matrix is positive. So we can blindly say, if all the minors are positive, two things are going to happen, which is the determinant of the matrix is positive, and also all the eigenvalues of the matrix are also positive. I am repeating it again. Suppose if all the minors of the matrix are positive, then two things are going to happen. The first thing is the determinant of the matrix is positive, and also all the eigenvalues are also positive. See, for identity matrix, all the elements in the diagonal are equal to 1. So therefore the eigenvalues of any identity matrix is equal to all the eigenvalues are 1. So therefore all the eigenvalues are equal to 1. So therefore if you want to figure out what is the determinant of this identity matrix, then it is equal to product of the eigenvalues. So is equal to, we will get 1. See, in other fashion also we can figure out the determinant of the identity matrix, which is A into A inverse is equal to identity. So do the determinant of the both sides. So we already know the determinant of A into B is equal to determinant of A into determinant of B. So therefore determinant of A into determinant of A inverse is equal to determinant of identity matrix. But we already know determinant of A inverse is equal to 1 by determinant of A. So therefore all these values will get cancelled. So therefore finally the determinant of the identity matrix is equal to unity. So in other fashion also I have figured out that determinant of identity matrix is equal to unity. See here another thing is rank of A into A transpose. I have already told you the rank of A is equal to rank of A transpose. But even if you do A into A transpose, the new matrix which we get after doing this product, then the rank of the new matrix is equal to rank of its original matrix A or the rank of the transpose matrix, because I already told you by doing the transpose, the rank of the matrix doesn't changes, because the rank itself tells the number of linearly independent rows or number of linearly independent columns. So just by doing that transpose, the number of linearly independent row vectors doesn't changes. So therefore the rank of the original matrix and the rank of transpose of the matrix are equal. See, another thing is determinant of A plus B. Suppose if you want to figure out what is the determinant of A plus B, it is not equal to determinant of A plus determinant of B. Suppose if you want to figure out A plus B determinant, in this fashion if you are figuring out determinant of A and determinant of B and doing the sum, then that is not equal to determinant of A plus B. This you need to remember. Suppose you can assume, like suppose I can figure out what is the transpose. By doing the transpose also we are doing for A transpose plus B transpose. In that fashion don't do for the determinant. The determinant doesn't hold in this way. Ax is equal to B. Suppose this is called equations, right? Linear equations, whether it can be a homogeneous equation or whether it can be a non-homogeneous equation. So here I want to figure out what is the unknown values are present in the x, right? So therefore x is equal to A inverse into B. Suppose the determinant of the matrix is not equal to 0, means this matrix is a non-singular matrix. Then we can tell that the solutions of this equations are unique solution. So if the determinant of the matrix is not equal to 0, then one thing is damn for sure, which is there is a unique solution for this all these equations which are present in this matrix form. And repeating it again, if the determinant of the matrix is not equal to 0, blindly one thing is possible, that is there is a unique solutions for all the equations which are present in this matrix. This equation can be either a homogeneous equation or whether it can be a non-homogeneous equation. For homogeneous, the matrix P is a zero matrix. For non-homogeneous equations, the matrix B is a non-zero matrix. Means at least one of the element in the matrix B is non-zero. See, if determinant of A is equal to 0, means we already know the determinant of the matrix is equal to product of the eigenvalues, correct? So if at least any one of the eigenvalues is 0, then we can blindly say that the determinant of the matrix is equal to 0. In another fashion, is equal determinant applies only for the square matrix. It is not for non-square matrix. Determinant property is not holds, not applied. So therefore, determinant of the matrix is equal to 0 only when at least one of the eigenvalue is 0. In another fashion also, the determinant of the matrix is equal to 0 means at least one of the eigenvalue is 0, and also one of the means there is some dependent vector, means dependent row vector or dependent column vector is present in that matrix. So that is the reason the determinant of the matrix is equal to 0. Means the determinant of the matrix is not equal to 0, means all the eigenvalues are non-zero. In another fashion also, all the row vectors or all the column vectors in that matrix are linearly independent. If they are linearly independent, the determinant of the matrix is not equal to 0 and all the eigenvalues are also non-zero. If some of the row vectors are dependent, we can damn for sure we can say that the determinant of the matrix is equal to 0 and at least one of the eigenvalue is also 0. See, here A put A to the power of theta is equal to A. This I have already told you. A to the power of theta means whether you do the first conjugate and do the transpose or whether you do the transpose and do the conjugate. Both the ways the result will be same. So for that, if it is equal to the original matrix, then we already know it is called as a Hermitian matrix. Or whether for the transpose matrix. For transpose matrix is A transpose is equal to a symmetric matrix. Whether for a Hermitian matrix or whether for a symmetric matrix, the eigenvalues are always real. This I have already told you in my previous lecture, which is the eigenvalues are always real for the two matrices. Whether the matrix can be Hermitian matrix or whether the matrix can be symmetric matrix. For these two matrices, always the eigenvalues are always real, means whether they can be positive, whether they can be negative, or whether they can be distinct or whether they can be equal. Anything can be possible. Lecture I have discussed about some of the points of the matrices in a detailed manner. In the remaining coming lectures also, I will discuss some of the points which are left over, and some of the points I have already told you in the previous lecture, but I am doing a repetition because it will be remembered. For during examination time also you can remember this one. If you like the content of our lectures, then please do like, share and subscribe to our YouTube channel, and don't forget to press the bell icon button so whenever you upload a new video, the direct notifications comes to your mobile. If any improvements in our video lectures, then please do comment in the comment section and we will definitely include all those improvements in the coming lectures. Thank you for watching this lecture. Keep smiling, take care and bye bye.